What do we really mean when we ask, what was there before the Big Bang? At first it sounds like a simple question, but the deeper you go, the stranger it becomes. Most people imagine nothing as empty space, quiet, black, and waiting. But physics tells us that even empty space is far from nothing. It's alive with energy, particles flickering in and out, and laws that continue to operate. The real puzzle is that in our best cosmological models, time itself begins with the Big Bang. If time has a starting point, then asking what came before may not even make sense. It's like asking what's north of the North Pole. Still, scientists don't stop there. They've explored ideas where the universe emerges from quantum fluctuations, where time stretches back through earlier cycles, or where the Big Bang wasn't the beginning at all, but just one chapter in a much larger story. Some models even suggest the universe could be finite, yet without boundaries, meaning no true before exists. So when we ask how nothing could exist before everything, we might be misled by language itself. The real question is, what conditions allowed our universe to begin? And does nothing ever truly exist at all? When people ask, how did nothing exist before the Big Bang? The very first step is untangling what nothing is supposed to mean. The word is simple in everyday life. If you open an empty box, you say there's nothing inside. If a bank account balance drops to zero, it's nothing in the sense of no money. But in physics, the word carries much heavier baggage, and it's often misleading. For most of us, nothing conjures up an image of blackness, emptiness, a void. But think carefully. That image itself isn't really nothing. It's space. It has dimensions, volume, and properties. If you could float in that imagined void, you'd still experience time ticking, and your body would still obey physical laws. That's not nothing. That's something. Even the vacuum of outer space, which seems empty, is far from it. A cubic centimetre of space contains quantum fluctuations, with particles constantly appearing and disappearing too quickly to be measured directly. The vacuum also carries energy, what physicists call zero-point energy, that can influence how particles behave. So when scientists talk about the vacuum, they're describing a restless background, not a true absence. Then there's another meaning, the absence of not just matter and energy, but also space and time themselves. This is where the question of before the Big Bang becomes so strange. If time itself began at the Big Bang, then talking about a state before is like asking for a time before time. It sounds grammatical, but it collapses logically. Philosophers add another twist. In everyday language, nothing is a placeholder, a way to describe absence. But true nothingness, a condition with no space, no time, no laws of physics, no potential for anything, is not something we can observe or even define consistently. The moment you describe it, you've already given it qualities, which means it's not really nothing. This is why physicists are cautious. Instead of nothing, they talk about specific conditions, a vacuum, a singularity, a fluctuation, or even the absence of classical time. Each of these is a something, even if it doesn't look like the universe we know today. So the real challenge is reframing the question. Instead of what existed before the Big Bang, a more precise way to ask might be, what physical state gave rise to the universe we see? Or, what do our best theories say about the earliest moment of existence? The shift from philosophy to physics doesn't erase the mystery, but it keeps us from getting trapped by language. To understand why nothing before the Big Bang is such a complicated idea, we need to look at how the Big Bang theory developed in the first place. It wasn't originally intended to explain the ultimate beginning of everything. It started as a model to explain observations in the 20th century that the universe was not static, but expanding. In 1929, Edwin Hubble made a striking discovery. By measuring the light from distant galaxies, he found that they were almost all moving away from us. The farther away a galaxy was, the faster it receded. This wasn't a sign that Earth was at the centre of the universe, but rather that space itself was stretching. Imagine dots on the surface of an inflating balloon. Each dot moves away from the others, not because they're travelling on their own, but because the balloon's surface is expanding. This discovery fit with Einstein's general relativity, which describes gravity not as a force pulling on objects, but as the curvature of space-time. Relativity predicted that the universe should be dynamic, either expanding or contracting. At first, Einstein resisted this idea and even inserted a cosmological constant to hold the universe steady. But after Hubble's findings, the expanding universe model became impossible to ignore. If the universe is expanding today, then logically, if you reverse the process, everything must have been closer together in the past. Keep running the clock backwards, and galaxies, stars, gas, and even radiation compress into an unimaginably dense, hot state. This led to the concept of a Big Bang, the universe beginning as an extremely compact point and then expanding into what we see now. By the mid-20th century, the Big Bang had strong support from observations. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, a faint glow spread across the sky. This radiation is the leftover heat from the early universe stretched into microwaves as space expanded. It was the smoking gun, showing that the universe really did emerge from a hot, dense origin. But the classical Big Bang model came with a sharp edge. If you follow the equations of general relativity back in time, the density and temperature increase without limit. At some finite point, they blow up to infinity. A singularity. The singularity is not a physical object sitting there. It's a sign that the mathematics of relativity breaks down. It means the theory stops being able to describe reality. At that singularity, space and time themselves are supposed to begin. That's where the familiar question arises. What happened before? According to the strict classical model, the question doesn't even make sense because there was no before. Time only exists after the Big Bang, so asking what came earlier is like asking for a position outside the edge of space. Still, even though the math of relativity pointed to a beginning, many physicists became uneasy with the idea of a true singularity. Singularities usually mean that the theory being used has reached its limit. In this case, it signaled that general relativity alone can't fully explain the origin. That's why the Big Bang in its classical form isn't treated as the final word, but as the beginning of deeper questions. The classical model successfully describes how the universe expanded and cooled, how light elements like hydrogen and helium formed in the first few minutes, and why we see the cosmic microwave background. But it doesn't tell us what started the expansion, or whether the singularity was a real physical event. That gap is where modern physics stepped in, proposing inflation, quantum cosmology, and other frameworks to smooth out the singularity and explore possible states before the Big Bang. Einstein's theory of general relativity is one of the most successful scientific frameworks ever created, but it is also one of the main reasons we find ourselves trapped in the puzzle of the Big Bang. To see why, it helps to step back and understand what general relativity actually says about the universe. In Newton's world, space and time were fixed, eternal backdrops. Time ticked at the same rate everywhere, without connection to matter or energy. Space was like an infinite stage, and time was the clock that measured the play. The universe could exist within this framework forever, expanding or contracting, but always inside this larger arena. Einstein broke that picture. He showed that space and time are not independent stages, but parts of the universe itself. They are dynamic. They bend and stretch depending on how matter and energy are distributed. That shift is more than a mathematical detail. It means that when we say the universe began, we're not just talking about matter and radiation springing into existence. We're talking about space and time themselves coming into being. Asking what came before the Big Bang is therefore like asking what lies outside space, or what time it was before time existed. The theory doesn't allow those questions to have answers, because the very concepts of outside and before are tied to the universe. When scientists use relativity to model the cosmos, they plug into the equations the average distribution of matter and energy in the universe. The solutions describe how the universe expands or contracts depending on its contents. Running the equations backward takes you to a moment when the density becomes infinite and the size of the universe shrinks to zero. That's the singularity. But the singularity is not a real place or event. It's a signal that the equations are breaking down. It's the mathematical equivalent of a car dashboard, light flashing red. It tells you something important is happening, but it doesn't give you the mechanics of the problem. This breakdown is why cosmologists are cautious. General relativity explains black holes, predicts gravitational waves, and underpins modern cosmology. But at the most extreme edges of reality, inside black holes and at the start of the universe, it ceases to work on its own. In those situations, quantum mechanics becomes essential because at very small scales, particles and energy behave in ways relativity cannot describe. The fact that relativity predicts infinities when pushed to the beginning of time is the clearest evidence that a deeper theory is needed. The problem of time sits at the center of this. In relativity, time is not universal. It flows differently depending on motion and gravity. Someone orbiting close to a black hole experiences time more slowly than someone far away. This has been experimentally confirmed many times. GPS satellites, for example, have to correct for both special and general relativity, because time ticks differently in orbit than on Earth's surface. These are small differences in practice, but they show that time is flexible, not absolute. If time can stretch and flow differently in our current universe, it raises a deeper issue. Did time even exist before the Big Bang? The equation suggests not. The beginning of time is tied to the beginning of the universe's expansion. There isn't an earlier moment to point to. For most physicists, this is not a satisfying endpoint, but rather a boundary telling us that general relativity is incomplete. Some physicists, including Stephen Hawking, argued that the question of before the Big Bang is as meaningless as asking what's north of the North Pole. The Earth's surface has a boundary at the pole, but there's no further direction to go. Similarly, the universe may have a boundary at the Big Bang, but no meaningful before. Others see this as a challenge, not a dead end. If relativity alone cannot answer the question, perhaps a theory that combines relativity with quantum mechanics, quantum gravity, will. What relativity does tell us with confidence is that time and space are not eternal frameworks stretching in both directions forever. They are features of the universe, intertwined with it. The moment you remove the universe, you remove time itself, and that means any talk of nothing before the Big Bang is immediately slippery. If before doesn't exist, then nothing may not either, at least not in any way we can describe with this theory. This is where we see the limits of relativity most clearly. It explains expansion. It explains curvature. It explains why galaxies move apart and why massive objects bend light. But when asked to explain the origin, it reaches a wall. Beyond that wall, we need new physics. And that is why the singularity problem and the nature of time have driven so many modern theories of the universe's beginning, from quantum cosmology to inflation to bouncing universes. Each of them starts with the recognition that relativity alone cannot tell the whole story. If general relativity forces us to accept that space and time themselves begin with the Big Bang, then the next natural question is, what does physics mean when it talks about nothing? Most people imagine a perfect emptiness. No matter, no light, no energy. But when you look at what modern physics says about empty space, you discover it is anything but empty. Quantum mechanics, the theory that governs the smallest scales of nature, paints a very different picture. Even in regions of the universe where there are no particles, no atoms, and no radiation, the vacuum is alive with activity. This is because of something called the uncertainty principle. According to quantum mechanics, you can never pin down both the energy and the timing of a system with perfect accuracy. If you try to force the energy of a vacuum to be exactly zero, then you lose all control over the timescale, and strange fluctuations become inevitable. What this means in practice is that so-called empty space is constantly seething, with temporary particle-antiparticle pairs flickering into existence and then annihilating each other almost instantly. These are known as virtual particles. They are not particles in the ordinary sense because they cannot be directly observed, but their effects are measurable. One famous example is the Casimir effect. If you place two uncharged metal plates extremely close together in a vacuum, they actually attract one another. This attraction isn't due to any charge or magnetism. It comes from the way quantum fluctuations are restricted between the plates. The pressure of vacuum energy outside the plates is slightly greater than inside, pushing them together. This is direct evidence that the vacuum is not empty. It has physical properties. Another striking example comes from black holes. Stephen Hawking showed that black holes aren't truly black. At their event horizons, quantum fluctuations can cause one particle of a virtual pair to escape while the other falls in. To an outside observer, the black hole appears to emit radiation, now called Hawking radiation. This process slowly drains energy from the black hole until, in theory, it could evaporate completely. Again, this relies on the fact that the vacuum is not nothing but a restless field, where energy and particles flicker in and out of existence. Physicists also talk about zero-point energy, the lowest possible energy state that a quantum system can have. Even if you remove all particles from a region of space, the energy cannot be reduced to absolute zero. There's always a residual jitter in the fields that permeate the vacuum. This background energy is not just a mathematical trick. It contributes to real, measurable effects. And here's where things take an even stranger turn. In modern cosmology, vacuum energy is linked to the cosmological constant, the mysterious factor in Einstein's equations that drives the accelerated expansion of the universe. Observations in the late 1990s showed that galaxies are not just receding from each other due to the initial push of the Big Bang. They are accelerating away, as though space itself is being stretched by a hidden energy. The best explanation we have today is that this is a property of the vacuum itself, so-called dark energy. In other words, what we might casually call nothing is actually the most dominant ingredient in the cosmos. This is why, when physicists say the universe might have arisen from nothing, they don't mean absolute nothingness in the everyday sense. They mean a quantum vacuum, a state with no ordinary particles, but still governed by physical laws, still filled with fields and potential energy. It's not a blank void, but a kind of stage where fluctuations can occur. Some cosmological models even suggest that a universe like ours could spontaneously emerge from such a vacuum, triggered by one of these fluctuations. Of course, this raises further puzzles. If the vacuum can give rise to universes, what determines the laws it follows? Where do the rules of quantum mechanics come from? And if the vacuum is everywhere, is it really fair to call it nothing? These are the kinds of questions that drive current debates in cosmology. But the key point is that when physicists use the word nothing, it's shorthand for something very different from what most people mean. In physics, nothing is never really nothing. It is at minimum a seething quantum vacuum filled with fluctuations and energy. The idea that the universe might have emerged from this kind of nothing is one of the most serious attempts to explain the origin of everything. Yet it also forces us to confront the uncomfortable possibility that the nothing of physics may just be another kind of something. By the late 20th century, the classical Big Bang model, even with its quantum vacuum ideas, ran into several deep puzzles. It could describe how the universe expanded from a hot, dense state, how light elements like hydrogen and helium formed in the first few minutes, and why there is cosmic microwave background radiation left over. But it couldn't explain why the universe looked the way it does. It left unanswered questions that seemed almost too neat to be coincidences. That's where inflation came in. Inflation was first proposed in the early 1980s by Alan Guth, and later refined by Andre Linde and others. The idea was simple in concept, but radical in implications. In the very earliest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid burst of expansion. Instead of expanding steadily from the beginning, space itself ballooned exponentially in a tiny sliver of time, smoothing out the cosmos in a way that solved several long-standing problems. One of those problems was the horizon problem. The cosmic microwave background radiation looks almost identical in every direction, with temperatures differing by only a few parts in 100,000. But according to the classical Big Bang model, regions on opposite sides of the sky should never have been in contact. They were too far apart to exchange light or heat. Inflation solves this by saying that those regions were once close together in a tiny, pre-inflationary universe, allowing them to equalize before being stretched far apart during inflation. Another issue was the flatness problem. Observations show that the universe is remarkably close to being geometrically flat, meaning its overall curvature is nearly zero. A flat universe is like walking on a vast plain. The rules of Euclidean geometry apply at large scales. But in the standard Big Bang without inflation, a perfectly flat universe would be highly unstable. Any small deviation would grow over time, making the universe either collapse quickly or expand uncontrollably. Inflation explains this by stretching space so much that any initial curvature gets ironed out, just like the surface of a balloon looks flatter as it inflates. Then there's the monopole problem. Grand unified theories of particle physics predict that the early universe should have produced massive, stable particles called magnetic monopoles. Yet no such particles have ever been observed. inflation provides an explanation. These relics would have been diluted to near invisibility by the enormous expansion, leaving the universe empty of them. The mechanics of inflation come from quantum field theory. The idea is that a special kind of energy field, often called the inflaton, dominated the early universe. For a brief period, this field remained stuck at a high energy level, creating a repulsive gravitational effect that drove exponential expansion. When the field eventually decayed to a lower energy state, inflation ended, releasing energy that reheated the universe and filled it with the particles and radiation that would later form stars and galaxies. This burst of inflation happened unimaginably quickly. In less than a trillionth of a second, the universe grew from subatomic scales to macroscopic ones, possibly larger than the visible universe today. To put it another way, if you took a proton and expanded it by inflation's factor, it would become larger than the observable cosmos. This staggering scale-up is what allows inflation to smooth and flatten the universe so effectively. One of the most important features of inflation is that it makes testable predictions. The small quantum fluctuations in the inflaton field would have been stretched by inflation into large-scale variations across the universe. These fluctuations became the seeds of structure, the tiny irregularities in density that, over billions of years, grew under gravity into galaxies and clusters. Observations of the cosmic microwave background by satellites like COBE, WMAP, and Planck show exactly this pattern of tiny ripples, strong evidence that inflation really did happen. Now, inflation also has strange consequences when you think about what happens at its edges. In many versions of the theory, inflation never completely ends everywhere. Instead, it stops in some regions, creating bubble universes like ours while continuing elsewhere. This process, called eternal inflation, means our universe may be just one bubble in a vast, possibly infinite multiverse. Each bubble might have different physical properties, different constants, even different laws of physics. Of course, inflation isn't universally accepted without criticism. Some physicists argue that it replaces one set of fine-tuning problems with another, since the inflaton field and its properties have to be chosen carefully to produce the universe we see. Others question whether inflation is falsifiable at all, or whether it slips into being more of a framework than a specific, testable theory. But despite these debates, inflation remains the leading explanation for why the universe looks the way it does. In short, inflationary cosmology takes us a step closer to answering the nothing question. Instead of the universe simply popping into being at the Big Bang, inflation suggests that our universe emerged from a brief but powerful process governed by physics. It doesn't solve the ultimate origin problem, where the inflaton came from, or why there are laws at all, but it provides a bridge between the quantum vacuum and the universe we see today. If general relativity breaks down at the Big Bang singularity, and inflation explains only what happens just after, then the natural next step is to ask, what happens if we combine relativity with quantum mechanics? This is the search for a theory of quantum gravity, a framework that describes both the smooth geometry of spacetime and the jittery, probabilistic nature of quantum fields. Without such a theory, we can't say much about the earliest moments of the universe, because we're trying to use tools that were never designed for those conditions. The challenge is that relativity and quantum mechanics operate with very different rules. Relativity treats space and time as continuous, smooth, and geometric. Quantum mechanics treats the world as discrete, probabilistic, and governed by uncertainty. Put them together and the math usually explodes into contradictions or infinities. Physicists have spent decades searching for a way to merge them. Out of this effort, several candidates for quantum gravity have emerged, each offering a different vision of what might have come before, or instead of, the Big Bang. One of the most discussed approaches is loop quantum gravity. In this theory, space-time itself is not continuous but made of tiny, discrete building blocks, a bit like pixels on a screen or atoms in matter. At the smaller scales, called the Planck scale, space and time are quantized. Instead of being infinitely divisible, they come in units. This quantization avoids the infinities that plague general relativity near the singularity. In cosmology, loop quantum gravity often predicts that the universe didn't begin from nothing, but from a prior contracting state. In other words, instead of a singularity, there is a bounce. The universe shrinks to a minimum size and then rebounds, expanding again. If this is correct, the Big Bang wasn't the birth of everything, but a transition between a collapsing universe and an expanding one. Another leading framework is string theory, which suggests that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings of energy. Different vibrations of these strings give rise to the particles and forces we observe. String theory naturally includes gravity, making it a strong candidate for unifying physics. In cosmology, string theory gives rise to scenarios where the Big Bang might not have been a beginning, but an event caused by the collision of higher dimensional objects called branes. In some models, two branes collide, releasing energy that ignites a hot, dense universe like ours. This is known as the ekpyrotic model. In such a view, before the Big Bang could be a higher dimensional cosmos with structures interacting in ways that occasionally trigger universes. Then there are causal set theories, which take the idea of discreteness even further. In these models, the fabric of spacetime isn't a continuous sheet, but a network of fundamental events ordered by cause and effect. Space and time emerge from this underlying structure, and the Big Bang might represent a transition in how these events organize, rather than an absolute beginning. Each of these quantum gravity approaches tries to deal with the central problem, the singularity predicted by relativity. Instead of an infinite density point, they replace it with something more physically meaningful, a bounce, a transition, or a higher dimensional interaction. These theories also have to connect back to the universe we observe today. They need to explain not only how the Big Bang began, but why the cosmos evolved into the smooth, structured universe that telescopes reveal. One of the reasons quantum gravity is so hard to test is that the conditions it describes are far beyond what we can reproduce in experiments. The Planck scale, where these effects dominate, is 20 orders of magnitude smaller than the nucleus of an atom. Particle accelerators like the Large Hadron Collider cannot come close to probing it. This means cosmology, looking at the largest scales of the universe, may be our best laboratory for testing these ideas. Subtle imprints in the cosmic microwave background, or signatures of gravitational waves from the very early universe, could one day help distinguish between these theories. What all of these approaches have in common is that they challenge the classical notion of nothing. In loop quantum cosmology, there is no empty nothingness before the Big Bang, only a prior universe contracting into a bounce. In string theory's brain-world models, before is filled with higher dimensional objects whose collisions spark universes. Even causal set theories replace nothingness with an underlying structure. Physics resists the idea of true nothing. Instead, it suggests that the Big Bang was a transformation, not an absolute beginning, and that before may have been just as real, though radically different from anything we know. By the early 1980s, some physicists began to wonder whether the question of before the Big Bang might be the wrong question entirely. If time is tied to the universe itself, then asking what happened earlier assumes there's a clock ticking outside of the cosmos, waiting for the universe to begin. Stephen Hawking and James Hartley put forward one of the boldest attempts to solve this puzzle, the no-boundary proposal. At its heart, the idea was to use quantum mechanics not just for particles, but for the entire universe. Instead of treating the universe's beginning as a sharp singularity, they suggested that the early universe could be described in terms of quantum probabilities. Just as an electron can exist in multiple possible states until it is measured, the universe itself could be thought of as a kind of quantum object with a set of possible histories. Hawking and Hartle introduced a mathematical trick called imaginary time. In our ordinary experience, time is a one-way arrow. It moves forward, and events unfold in sequence. But if you replace time with a mathematical version that behaves more like a spatial dimension, something strange happens. The singularity at the Big Bang disappears. Instead of a sharp edge or a beginning point, the universe takes on the shape of something finite but without boundaries, much like the surface of a sphere. A sphere has a finite area, but if you walk around on it, you never encounter a sharp edge. You just keep going. In this analogy, time at the beginning of the universe doesn't start with a hard boundary. It smoothly transitions, avoiding the singularity. This doesn't mean time is literally imaginary in the everyday sense. It's a mathematical way of saying that in the earliest phase of the universe, the distinction between space and time may not have been as rigid as it is now. The cosmos could have been in a state where the usual concepts of before and after didn't exist. Only as the universe cooled and expanded did time emerge in the familiar sense we know? The no-boundary proposal has a striking implication. The universe doesn't need an external cause or a moment of creation in the way we usually imagine. If time is finite but unbounded, there is no point at which you can say, here is the start. The universe is self-contained. It simply exists with no requirement for a before. Of course, this is a deeply counterintuitive idea. People are used to beginnings and causes. Everything we encounter in daily life has a moment when it starts. A fire when the match is struck, a storm when clouds collide, a child when conceived. To imagine the universe as something that doesn't have a sharp beginning is to step outside those patterns. Hawking himself compared it to asking what's north of the North Pole. The question only arises if you assume a boundary where none exists. Critics of the no-boundary idea point out that it is difficult to test. Like many proposals in quantum cosmology, it depends on mathematics that goes far beyond current experiments. The mathematics itself is elegant, but elegance is not proof. What we can say, though, is that the proposal removes the necessity of a singularity and provides a way of thinking about the universe that avoids the trap of before. One of the appealing features of the Hartley-Hawking model is that it blends the probabilistic nature of quantum mechanics with the geometry of general relativity. Instead of the universe springing from nothing in a singular, sharply defined event, it comes into being as one history among many possible ones. The fact that we observe this universe may be the result of probabilities favouring histories that allow for structure, galaxies and observers like us. Whether or not the no-boundary proposal turns out to be correct, it represents a profound shift in perspective. It tells us that the beginning of the universe may not be a singular bang at all, but rather a smooth quantum transition. And if that's the case, then the mystery of nothing before the Big Bang dissolves. There was never a before in the first place. The vacuum fluctuation hypothesis is one of the boldest attempts to take quantum mechanics seriously when applied to the entire cosmos. The basic idea is deceptively simple. What if the universe itself is just a quantum fluctuation? In quantum physics, fluctuations are unavoidable. Even when you remove every particle and strip away all visible energy, the vacuum is never truly empty. It seethes with short-lived virtual particles, fields, and energy blips, all dictated by the uncertainty principle. These fluctuations happen constantly on microscopic scales. Normally, they cancel out or disappear almost instantly. But the hypothesis suggests that, under the right conditions, a fluctuation could grow rather than vanish, expanding into a universe like ours. One way physicists think about this is to imagine the vacuum as a sea of energy fields. In most places, the fluctuations remain small, but occasionally one could tunnel into a new state, triggering an expansion. This process is somewhat like radioactive decay, where a nucleus suddenly jumps into a different configuration. Instead of producing a new particle, though, the vacuum fluctuation would produce an entire universe. This is not just speculation. In the 1970s and 1980s, physicists like Edward Tryon, Alexander Vilenkin, and others seriously proposed that the universe could have been a quantum fluctuation of nothing. Tryon argued in 1973 that the total energy of the universe might actually be zero. At first that sounds absurd. After all, galaxies, stars, and planets clearly contain immense amounts of energy. But in relativity, gravity itself carries negative energy. The positive energy of matter and radiation could be exactly balanced by the negative gravitational energy of the expanding universe. If that balance holds, then the entire universe might be a net, zero-energy system. And in quantum mechanics, systems with zero net energy can fluctuate into existence without violating conservation laws. If this is true, then the universe doesn't need an external cause or a starting push. It could arise spontaneously out of the quantum vacuum. Inflation, which we explored earlier, actually makes this idea more plausible. A tiny fluctuation could rapidly inflate into a macroscopic universe. Without inflation, such a fluctuation might fizzle back into nothingness. With inflation, it becomes stable and lasting. There are obvious questions, though. If universes can fluctuate into existence, why this one? Why do the laws of physics have the particular form they do? Why does our vacuum allow such fluctuations at all? The vacuum fluctuation hypothesis doesn't fully answer those questions. It just provides a mechanism for how something can come from what looks like nothing, provided you understand nothing in the quantum sense. Skeptics also point out that while quantum fluctuations are well studied on microscopic scales, applying the same logic to the entire universe is a huge leap. Quantum mechanics usually describes events within space and time, but the universe itself includes space and time. So can we even talk about a fluctuation happening if time itself is part of what's being created? This is one of the deepest puzzles in trying to extend quantum ideas to cosmology. Nevertheless, the vacuum fluctuation hypothesis remains compelling because it offers a concrete way to connect the language of quantum physics with the existence of the universe. Instead of invoking an external cause or an undefined singularity, it suggests the cosmos emerged naturally from the physics of the vacuum itself. It reframes nothing as a seething quantum background full of potential, where universes are not only possible, but perhaps inevitable. If true, this would mean our universe is not a miraculous exception, but one of countless possible fluctuations. Most would fade instantly, but once in a while, one inflates into a universe capable of lasting billions of years and forming stars, galaxies, and life. That possibility reshapes the way we think about nothingness. It is not a void to be puzzled over, but a fertile ground of probabilities, where existence itself can emerge spontaneously. If inflation could happen once, why not more than once? This question led physicists to consider one of the most sweeping possibilities in modern cosmology, that our universe might be just one of many. This is the idea of the multiverse. It's not science fiction. It arises naturally from theories like eternal inflation and string theory, and it changes how we think about the question of nothing. Eternal inflation comes directly from the inflationary model we explored earlier. Inflation is driven by a field with a very high energy state, and while it decays in some regions to end inflation and produce normal universes like ours, in other regions it continues forever. Space keeps expanding exponentially in a patchwork process, with pockets where inflation ends becoming bubble universes. Our universe could be one such bubble, surrounded by an endlessly inflating sea, where other bubbles are constantly forming. Each bubble might have its own physical constants, its own versions of matter and energy, and possibly its own versions of space and time. In this picture, the Big Bang wasn't the absolute beginning. It was just a local event that started our universe's expansion. The larger process of eternal inflation has no true beginning or end. It just keeps generating universes. If this is right, then asking what came before our Big Bang is like asking what came before one droplet in a rainstorm. The droplet has a start, but the storm itself has been ongoing. String theory provides another route to a multiverse. It suggests that the fundamental ingredients of reality are tiny vibrating strings, and the way these strings vibrate depends on the shape of hidden extra dimensions. The mathematics of string theory allows for an astonishingly large number of possible vacuum states, different ways the extra dimensions could be curled up. Each configuration could produce a universe with different laws of physics. This collection of possible universes is sometimes called the string landscape. If inflation can generate many universes, each one could land in a different region of this landscape, meaning the constants of nature vary across the multiverse. This idea helps explain one of the deepest mysteries in cosmology, why our universe seems so finely tuned for life. For example, if the strength of the electromagnetic force or the mass of the electron were even slightly different, chemistry as we know it wouldn't work. If the cosmological constant were larger, the universe would expand too quickly for galaxies to form. In a multiverse, these values aren't tuned at all. They're just different in different universes. We happen to live in one of the rare universes where conditions allow observers to exist. This is sometimes called the anthropic principle. Of course, the multiverse raises as many questions as it answers. If there are countless other universes, can we ever detect them? They would be separated from us by inflating space, unreachable in principle. Some physicists argue that if the multiverse makes no observable predictions, it belongs more to philosophy than science. Others counter that traces of collisions between bubble universes might be imprinted faintly in the cosmic microwave background, offering indirect evidence. Searches for such signals are ongoing, though no clear detection has yet been made. The multiverse also shifts the question of nothing. If there is an endless background of inflating space constantly producing universes, then nothing never really exists at all. There is always a larger something, an eternal process of creation. In this sense, our Big Bang's just a local event within a much grander structure. What we thought of as nothing before our universe might simply be the inflating backdrop or higher dimensional space in which universes are born. Some scientists embrace this as the most natural explanation for the universe's properties. Others worry it undermines the search for deeper principles. If everything that can happen happens somewhere in the multiverse, then perhaps the universe doesn't need deeper explanation. Our world is just one among an endless set. For some, that feels unsatisfying. For others, it is an elegant resolution. Either way, the multiverse forces us to rethink the concept of before and nothing. Instead of imagining a lonely void waiting for the Big Bang, we may be part of an infinite cosmic foam, where beginnings are local but the larger process has no start and no end. At this point, a deeper question starts to emerge. Even if we accept ideas like inflation, vacuum fluctuations, or a multiverse, we still face the puzzle of the rules themselves. Where do the laws of physics come from? Why do they exist at all? If the universe is a something born from nothing, then what gave that nothing its structure? One way physicists approach this is through the idea of symmetry. In physics, symmetry doesn't mean something is pretty or balanced in the everyday sense. It means that the laws of physics look the same under certain transformations. For example, if you slide a billiard table a few feet to the left and repeat an experiment, the results don't change. This is translational symmetry. If you rotate a spinning top and it behaves the same, that's rotational symmetry. These symmetries aren't just mathematical curiosities, they are deeply connected to conservation laws. For instance, the fact that energy is conserved is directly linked to time symmetry. The laws of physics don't change as time goes on. The early universe appears to have been governed by an even higher degree of symmetry than we see today. At very high energies, it's thought that the fundamental forces of nature, gravity, electromagnetism, the weak force and the strong force, may have been unified. As the universe cooled, this symmetry broke, leaving behind the distinct forces we observe now. This process is a bit like water freezing into ice. The liquid looks the same in every direction, but when it crystallizes, patterns emerge and the symmetry is reduced. The early universe might have undergone similar phase transitions, breaking high symmetries into the lower symmetries of today. This raises an intriguing idea. If the laws of physics can change as symmetries break, then perhaps the laws themselves are not absolute. They may have evolved from a simpler, more unified state. In some theories, different regions of the multiverse may have different broken symmetries, which would explain why the laws of physics appear fine-tuned in our universe. We live in a region where the symmetry breaking led to conditions that support complexity and life. But that still doesn't answer the ultimate why. Why do the laws exist in the first place? Why does mathematics describe reality so effectively? This is where physics brushes up against philosophy. Some physicists argue that the laws of physics simply are. They don't need an explanation. They are the foundation. Others suggest that the laws themselves might be emergent, arising from a deeper underlying structure we don't yet understand. For instance, some versions of quantum gravity hint that space-time itself, and perhaps the laws governing it, could emerge from more fundamental relationships. There is also the question of whether the laws of physics are prescriptive or descriptive. Do they dictate how the universe must behave, or are they patterns we humans have discovered that happen to describe how reality works? If the latter, then perhaps asking, where do the laws come from, is like asking, where does the rule that triangles have 180 degrees come from? The rule isn't imposed on triangles, it's simply true by definition. Similarly, the laws of physics might be unavoidable consequences of the structure of reality. This ties into the concept of mathematical inevitability. Some thinkers, like Max Tegmark, propose that mathematics is reality, that the universe exists because mathematical structures exist, and any consistent mathematical system corresponds to a physical reality. In this view, the laws of physics don't come from anywhere. They are simply the mathematical truths of the structure we happen to inhabit. Our universe exists because it is one of those possible structures. The symmetry of the early universe, the emergence of forces, and the apparent inevitability of certain patterns suggest that what we call nothing might never have been lawless. Even in the absence of matter, energy, or space, the underlying framework of possible rules could still exist. And that means the question of how nothing became something might not be the right way to phrase it. Instead, we might say that the laws of physics are what make it impossible for nothing to exist at all. The idea that mathematics might not just describe reality, but actually be reality, is one of the most provocative proposals in modern cosmology. It's called the mathematical universe hypothesis, most closely associated with physicist Max Tegmark. It pushes us to reconsider what we mean when we say the universe exists, and it offers a radical angle on the problem of how nothing could exist before the Big Bang. At first glance, mathematics feels like a tool. We use it to measure distances, calculate orbits, or predict particle interactions. But when you look closely at the history of science, mathematics hasn't just been a tool. It has revealed patterns in nature with uncanny accuracy. Newton's equations described the motions of the planets. Maxwell's equations predicted electromagnetic waves before anyone had detected them. Einstein's equations of relativity predicted black holes and gravitational waves decades before technology confirmed them. Over and over, mathematics written on a chalkboard has turned out to describe the fabric of reality itself. This unreasonable effectiveness of mathematics, as Eugene Wigner once called it, suggests something deeper may be going on. Why should abstract symbols invented in human minds match the workings of the cosmos so perfectly? The mathematical universe hypothesis takes this mystery seriously. It suggests that the universe is not just described by mathematics, it is mathematics. Every consistent mathematical structure exists, and our physical universe is simply one of them. If this is true, then the question, what was before the Big Bang, changes form. Instead of asking what preceded the physical universe in time, we ask why this particular mathematical structure is the one we inhabit. In Tegmark's framework, there's no special reason. Every possible mathematical structure corresponds to a universe. We just happen to live in one that allows self-aware structures, like humans, to exist and ask these questions. In this view, nothing doesn't exist because all consistent structures exist, timelessly, in the mathematical sense. This sounds abstract, but it connects to real physics. Consider the constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant. They seem arbitrary, yet precise enough to allow life. If the universe is a mathematical object, these constants are simply properties of the structure we're in. Other universes, corresponding to different mathematical structures, would have different constants, or no recognizable matter at all. Critics of the mathematical universe hypothesis argue that it isn't testable. If every mathematical structure exists, how do we make predictions? Tegmark responds by pointing out that we can make statistical arguments. If we expect to find ourselves in a universe that allows life, then certain values of constants should be more likely. For example, if most mathematical structures produce universes with no complexity, the fact that we find ourselves in one with complexity is already a clue. The hypothesis also reframes the idea of creation. In a mathematical universe, there is no moment of emergence from nothing. The universe simply is, as a timeless mathematical truth. Just as the Pythagorean theorem was true long before any human discovered it, our universe's underlying structure exists independently of time. The Big Bang, in this view, is not the creation of the universe, but the unfolding of one aspect of its mathematical nature. This perspective is unsettling because it strips away the sense of contingency. In ordinary physics, we ask what caused the Big Bang, or why the laws of physics are as they are. In the mathematical view, there is no why. There is only the fact that consistent structures exist, and we are inside one of them. Nothing, in the everyday sense, a state with no rules, no structures, no mathematics, is impossible. If mathematics exists necessarily, then so do the universes it describes. Whether or not the mathematical universe hypothesis is true, it shows how far the concept of nothing can shift when examined through physics. The vacuum isn't nothing. The absence of time isn't nothing. And maybe even mathematics itself is never nothing. It's the ultimate something, a foundation that cannot be erased. When we talk about the beginning of the universe, we often focus on space, time, matter, and energy. But there's another ingredient that can't be ignored: entropy. Entropy is the measure of disorder in a system. Or more precisely, the number of ways a system can be arranged. In everyday life, entropy tends to increase. Ice melts into water. Eggs break but don't spontaneously reassemble. Smoke disperses into the air. This is the second law of thermodynamics. The universe as a whole drifts toward higher disorder. The strange thing is that our universe seems to have started in an extraordinarily low entropy state. At the moment of the Big Bang, matter and energy were compressed into a hot, dense form. You might think this would mean high entropy, since everything was mixed together. But in terms of gravity, the opposite is true. The most disordered state for matter under gravity is clumped, not smooth. Think of sand poured into a pile. The pile is the natural state. A completely uniform distribution is special and unstable. So the fact that the early universe was smooth, with only tiny ripples in density, means it began in a highly ordered, low entropy condition. This is one of the deepest puzzles in cosmology. Why would the universe start so improbably ordered? If nothing before the Big Bang really meant randomness or chaos, then we'd expect a high entropy beginning. Instead, the Big Bang set the stage for a universe that could develop stars, galaxies, and eventually life. All of which rely on the increase of entropy over time. The arrow of time itself is tied to this. We experience time as flowing in one direction. The past is different from the future, but the fundamental laws of physics are almost all reversible. If you film two particles colliding and play the video backward, the equations don't care. It looks just as valid. What makes time flow one way is entropy. We remember the past and not the future because entropy was lower in the past and increases toward the future. Without that gradient, time would lose its meaning. So why did the universe begin with such low entropy? Some physicists argue that inflation helps explain this. By stretching the universe rapidly, inflation could have smoothed out irregularities and left behind a nearly uniform low entropy state. Others counter that inflation itself needs special initial conditions to get started, so it shifts the problem rather than solves it. Roger Penrose, one of the pioneers in this area, has argued that the entropy puzzle is central to understanding the Big Bang. He suggests that the very smoothness of the early universe represents a deep mystery, one that standard cosmology doesn't resolve. If entropy is the true measure of disorder, then the universe didn't emerge from a chaotic nothing. It emerged from an exquisitely fine-tuned beginning. This leads to strange consequences if we take the laws of probability seriously. In statistical mechanics, the most likely way to get a low entropy state in a universe that runs forever isn't to start the whole cosmos in order. It's to have small, localized fluctuations. The most extreme version of this argument is the idea of Boltzmann brains, self-aware entities that randomly fluctuate into existence out of chaos, complete with false memories of a past that never existed. While this is a logical consequence of certain views, most physicists find it absurd. After all, we see a vast, coherent universe, not just isolated conscious fluctuations. Still, the fact that this argument arises shows how strange entropy is when applied to the universe as a whole. The thermodynamic puzzle is another way of saying that nothing doesn't explain what we see. If the universe began from true nothing, why did it start in such a special state? Why didn't it begin in maximum disorder? Instead of chaos, the Big Bang gave us an orderly launch pad that allowed complexity to grow. That order, encoded in the low entropy of the early cosmos, may be as fundamental to the mystery of existence as the laws of physics themselves. One of the strangest lessons of modern cosmology is that nothing itself has energy. This realization goes back to Einstein's equations of general relativity. When he first developed them, the equation suggested that the universe couldn't just sit still. It would either expand or contract. Since this conflicted with what he and most scientists of his time assumed, a static, eternal cosmos, Einstein added an extra term to his equations, the cosmological constant. This constant acted like a repulsive force built into space itself, countering gravity to hold the universe steady. When Edwin Hubble discovered the expansion of the universe in 1929, Einstein famously abandoned the cosmological constant, calling it his biggest blunder. For decades afterward, most cosmologists assumed it wasn't needed. But the universe had one more surprise in store. In the late 1990s, two teams studying distant supernovae found that not only was the universe expanding, it was expanding faster and faster. Instead of slowing down under the pull of gravity, galaxies were accelerating away from each other. The discovery stunned the scientific community. The best explanation was that some form of energy, intrinsic to space itself, was driving this acceleration. Suddenly, Einstein's discarded cosmological constant was back in the picture. Today we call this phenomenon dark energy. It makes up about 70% of the total energy content of the universe. Unlike ordinary matter and radiation, which dilute as the universe expands, dark energy seems to remain constant in density. As space grows, there's more of it, so its influence actually increases over time. That's why the expansion of the universe has shifted from slowing down to speeding up. This has profound implications for the concept of nothing. Empty space, which most of us would instinctively call nothing, turns out to be one of the most powerful forces in the cosmos. Even in a perfect vacuum with no particles, dark energy is there, woven into the structure of space-time itself. If you remove all matter, all radiation, and all fluctuations, the vacuum still has energy. And that energy shapes the destiny of the entire universe. One way to think about this is to imagine stretching a rubber sheet. The sheet isn't just a neutral backdrop. It resists being stretched, and its properties matter for how things move on it. Space itself is like that, except instead of resisting expansion, dark energy drives it. Our universe is not simply coasting outward from the Big Bang, it is being pushed apart by the energy of the vacuum. The discovery of dark energy also links back to the idea of the cosmological constant. In relativity, the constant can be interpreted as a property of space itself. But when physicists try to calculate the vacuum energy using quantum field theory, the result is a disaster. The predicted value is about 120 orders of magnitude larger than what we actually observe. This mismatch is often called the cosmological constant problem, and it is arguably the biggest unsolved problem in theoretical physics. Why is the vacuum energy so small but not zero? Why does it have the value that allows galaxies, stars, and life to exist? In the context of our question about nothing, this is especially striking. It suggests that even the barest possible state of reality is not an empty void, but a structured medium with measurable properties. The so-called nothing before the Big Bang may not have been nothing at all. It may have been a quantum vacuum imbued with this dark energy. Dark energy also shapes the universe's future. If it continues to act the way it does now, the expansion will accelerate forever, pushing galaxies farther apart until distant ones disappear from view. Trillions of years from now, observers in our galaxy might see only the local group of stars, with everything else stretched beyond visibility. In that far future, the universe would look almost empty again, though in reality it would still be dominated by dark energy. So the cosmological constant tells us something profound. Nothingness is unstable. Space itself carries energy, and that energy influences the cosmos on the largest scales. Far from being a neutral backdrop, nothing is one of the most active players in the story of the universe. Physics has taken us deep into the mechanics of how the universe could have begun, through relativity, quantum fluctuations, inflation, or multiverse scenarios. But at some point, the question of nothing strays into territory that physics alone can't settle. Here is where philosophy steps in. Humans have wrestled with the concept of nothingness for millennia, long before cosmology became a science. The ancient Greek philosopher Parmenides famously argued that nothing is impossible. If nothing exists, it is already something, because we're speaking of it. This paradox haunted philosophy for centuries. Aristotle agreed. In his view, nature abhors a vacuum. The universe, in classical thought, was eternal. There could be no absolute nothingness because the cosmos had always existed. Religious traditions took the idea in a different direction. The Judeo-Christian concept of creatio ex nihilo, creation out of nothing, made nothing central to theology. In that view, the universe had a beginning, and it came from no pre-existing matter or structure, only divine will. Other traditions, such as some Hindu and Buddhist philosophies, viewed the universe as cyclical, with no ultimate beginning. For them, nothingness was less a void and more a transition between states, part of an eternal rhythm. Modern philosophy continues to debate whether nothing can even be coherently defined. Is it the absence of space and time, the absence of physical laws, Or is it an incoherent concept, a placeholder word for something we can't really imagine? If we say that nothing existed before the Big Bang, are we making sense, or are we disguising ignorance with language? This tension is clear in the way scientists use the word. When cosmologists speak of the vacuum or quantum fluctuations, they are not describing absolute nothing, but a special kind of something. An arena with rules, probabilities, and potential. Critics argue that calling this nothing is misleading. It's like emptying a house of furniture but leaving the walls and foundation, then declaring the house nothing. Something is always left behind. The philosophical challenge is that even if physics provides a mechanism for the universe's emergence, it doesn't explain why there is a mechanism in the first place. Why are there laws of physics instead of no laws? Why is there a quantum vacuum instead of nothing? These questions are not testable in the laboratory. They press against the boundary where science meets metaphysics. Some philosophers argue that nothing is literally impossible. To say there was nothing already smuggles in the idea of existence, because nothing is still being thought about as a state. Others, like Martin Heidegger, framed it differently. The real mystery is not why there is nothing, but why there is something instead of nothing. This question, perhaps unanswerable, continues to echo in both philosophy and cosmology. The debate also ties into human psychology. Our brains are wired to think in terms of cause and effect. We see events as having origins, and we struggle with the idea of a causeless beginning. When we imagine nothing, we project our everyday experiences of emptiness, an empty room, an empty sky, onto a cosmic scale. But those everyday images are still forms of something. True nothingness, stripped of all structure, may be beyond what human minds can really grasp. In the end, philosophy reminds us that the word nothing carries baggage. It might not point to a real possibility at all, or it might point to something deeper than science currently allows us to test. Either way, the concept keeps forcing us back to the central mystery. Is it coherent to talk about nothing, or is the very question flawed? One of the biggest obstacles in asking how nothing could exist before the Big Bang is that we're trapped by language. Words evolved for everyday life, hunting, building, trading, not for describing the birth of the universe. When we use a simple, common word like nothing, we carry with it assumptions that don't translate into physics. In ordinary speech, nothing is easy to picture. It's an empty glass, a silent room, a blank page. But none of those examples are truly nothing. An empty glass still has air molecules, or at least the container itself. A silent room still has space, walls, and perhaps the faint hum of background noise. Even a blank page is something, a sheet of paper made of atoms. What we call nothing in daily life is always an absence of one thing in the presence of many others. Physics magnifies this problem. In quantum mechanics, a vacuum sounds like nothing, but it is alive with energy and fluctuations. In cosmology, before the Big Bang sounds like a time when nothing existed, but relativity tells us there may not even be a before. The words we use create questions that the universe itself may not pose. That's why some scientists argue that asking, what was before the Big Bang, is like asking, what's north of the North Pole? The question has grammar but no meaning. It tricks us into chasing a phantom, because the very word before assumes a timeline that might not exist without the universe itself. Similarly, when we ask why did nothing turn into something, we may be smuggling in an assumption that there ever was a state of absolute nothingness to begin with. The semantic trap doesn't just confuse laypeople, it confuses professionals too. Even in scientific papers, phrases like the universe from nothing or creation out of nothing are used, but the nothing in those contexts always has hidden structure. It might mean a quantum vacuum, a higher dimensional space, or a probabilistic state in which universes can emerge. Those are all somethings with rules and frameworks, not pure absence. But because our language doesn't easily distinguish between these shades of emptiness, we collapse them all into one misleading word. This is not to say the question is meaningless. It's meaningful in the sense that it exposes the limits of our understanding. But it may be that the puzzle of nothing is partly an artifact of how humans think and speak. We are used to opposites. Light versus dark, full versus empty, something versus nothing. The cosmos may not fit neatly into those binary categories. The real challenge, then, is to refine the question. Instead of, how did nothing exist before the Big Bang? We might ask, What is the most stripped-down state of reality that physics allows? Or, what physical framework can exist without space, time, or matter as we know them? Those questions are still profound, but they're not tangled in the everyday illusions that language creates. So part of the difficulty isn't just in the science, it's in our words. The way we frame the problem may be pointing us in circles. If we want to get closer to understanding, we may need to abandon nothing as a term altogether and replace it with concepts that physics can define clearly. Otherwise, we risk being trapped by semantics, debating endlessly about a word rather than the reality behind it. Even with all the theories on the table, relativity, inflation, quantum gravity, multiverse ideas, and philosophical takes, we keep hitting the same wall. Limits. Science has advanced enormously in explaining the universe after the first fractions of a second. But when it comes to the ultimate origin, we are still in the dark. Understanding those limits is important because it tells us what questions physics can answer now, what might be answerable in the future, and what might remain beyond reach. One of the clearest limits comes from observations. We can only see back so far in time. Light from the earliest stages of the universe is hidden behind a veil. The farthest back we can look directly is the cosmic microwave background radiation, about 380,000 years after the Big Bang. Before that, the universe was opaque, a plasma of particles scattering photons constantly. We can infer earlier conditions using physics, but we don't have direct access to data. That leaves us with models and probabilities rather than direct measurements. Another limit is energy. To truly probe the Planck scale, the unimaginably small scale where quantum gravity would dominate, we would need particle accelerators, many orders of magnitude, more powerful than anything we could ever hope to build. The Large Hadron Collider, the most powerful machine on Earth, is still laughably far from reaching the required energies. In practice, this means we can't create the conditions of the early universe in a laboratory. We rely instead on indirect signatures, like tiny ripples in the cosmic microwave background, or the potential detection of primordial gravitational waves to give us hints. Then there is the issue of testability. Many proposals, eternal inflation, multiverse models, string landscapes, are compelling, but they may not be testable even in principle. If other universes exist but are forever cut off from ours, do they count as scientific explanations? Some physicists say yes because the mathematics naturally predicts them. Others argue that without observational evidence, these remain speculative frameworks, more like philosophy than physics. Quantum cosmology also faces a limit in interpretation. Equations can be written that describe a universe emerging from a quantum state, but interpreting what that means in plain language is fraught with problems. If time itself is part of the universe, then what does it mean for a process to happen before time? If probabilities govern the birth of universes, what do probabilities mean when there is no external clock to measure them against? These questions blur the boundary between science and semantics. There are also unknowns hidden in plain sight within our current universe. Dark matter makes up about 25% of the cosmos, yet we don't know what it is. Dark energy makes up 70%, yet we don't know why it exists or why it has the value it does. Until we understand these dominant components of the universe, any claim about its ultimate origin rests on shaky ground. Our picture of reality is still incomplete, and the missing pieces could radically alter how we think about beginnings. Some scientists embrace these limits as temporary. History shows that boundaries often crumble as technology advances. A century ago, no one could have imagined detecting gravitational waves. Yet today we have observatories listening to the universe's most violent events. Perhaps one day we will see subtle imprints of the earliest moments of the cosmos, encoded in gravitational waves or in patterns of matter distribution. These could provide crucial clues about what really happened at the boundary of time. Others argue that certain questions may remain forever outside science. The problem of why there is something rather than nothing may be inherently untestable. If we can't, in principle, access evidence for or against a proposition, then science may have to stop at the line and admit its limits. That doesn't make the question meaningless. It just places it in the realm of philosophy rather than empirical physics. The truth is we don't know which limits are temporary and which are fundamental. The edge of the Big Bang may be like the horizon of our vision. As we move closer, new vistas appear. Or it may be like the horizon of a black hole, a boundary beyond which no further information can be obtained. Either way, Acknowledging what we don't know is not weakness. It's the honest position of science, which advances by testing, questioning, and recognizing where knowledge ends. For much of the 20th century, the Big Bang was interpreted as a true beginning, a singular point where time, space, and matter came into existence. But many physicists have never been comfortable with that notion. A singularity, after all, is a breakdown of equations, not necessarily a description of reality. This unease has fueled a wide range of models in which the universe has no absolute start, only transitions, cycles, or transformations. One of the oldest alternatives is the cyclic universe. In this picture, the cosmos expands, slows, and eventually contracts back down, leading to a big crunch. From that crunch, a new expansion begins. The universe could go through endless cycles of birth, death, and rebirth. This idea has ancient roots in philosophy and mythology, but modern versions rely on physics. For example, some adaptations of loop quantum gravity predict that instead of collapsing into a singularity, the universe bounces. A contracting phase reaches a minimum scale, then rebounds into an expanding phase, like the one we live in today. In that sense, the Big Bang wasn't the first bang, just the most recent bounce. Another approach comes from string theory in the form of ekpyrotic models. These suggest that our universe may be one of two higher dimensional branes floating in a larger space. Every so often these branes collide. Each collision looks to us like a big bang, filling the universe with energy and matter. But in reality, it's just one event in a repeating cycle of impacts. From this perspective, the Big Bang's not a unique beginning, but one in a series of cosmic resets. There's also Roger Penrose's conformal cyclic cosmology. Penrose argues that the remote future of the universe, dominated only by radiation and black holes, could be stretched and rescaled into something indistinguishable from the Big Bang. In this model, what we think of as the beginning may actually be the continuation of a previous aeon. Each universe expands until matter is diluted, black holes evaporate, and only radiation remains. Then, in the mathematics of conformal geometry, this featureless, infinite future maps onto a new Big Bang, starting the cycle again. Penrose has even suggested that faint circular imprints in the cosmic microwave background might be the fingerprints of black holes evaporating in the aeon before ours, though this claim remains controversial. Even outside these specific theories, many physicists believe the concept of a true beginning is suspicious. In physics, infinities almost always signal that a theory is incomplete. Why should the entire universe be an exception? The idea of a no-beginning universe replaces the singularity with a more continuous process, whether through bounces, cycles, or emergent phases where time itself behaves differently. These scenarios also shift how we think about nothing. If the universe is eternal in some form, then there never was absolute nothingness. There were always conditions of some kind, perhaps radically different from our own, but never the pure void we imagine in casual conversation. In a cyclic universe, before our Big Bang was just a contracting cosmos. In a brane collision, it was higher dimensional objects in motion. In Penrose's conformal model, it was the long, stretched-out end of a previous aeon. None of these leave room for literal nothing. Critics of no-beginning ideas argue that they may just push the problem back, rather than solve it. If cycles repeat, why is there a cycle at all? If branes collide, where did the branes come from? But supporters counter that replacing a singularity with an ongoing process makes more sense, because it eliminates the need for an absolute boundary. The universe may not have an ultimate origin in the way we imagine, but instead be part of an eternal chain of transformations. Whether or not any of these models turn out to be correct, they highlight an important point. The Big Bang might not be the beginning of everything. It may only be the beginning of our observable universe, the latest chapter in a much longer and perhaps unending story. Right now in 2025, the question of what came before the Big Bang, or whether that question even makes sense, is one of the hottest frontiers in cosmology. For all the philosophical debates and speculative theories, research is steadily advancing, guided by new data from telescopes, satellites, and mathematical work in theoretical physics. While we don't have final answers, the landscape of ideas today is more refined than ever. One of the most powerful tools in this effort is the Cosmic Microwave Background, CMB. Since the COBE satellite in the early 1990s, followed by WMAP and Planck, Scientists have been mapping the faint radiation left over from about 380,000 years after the Big Bang. The CMB is like a baby picture of the universe, showing us its earliest observable state. In 2025, researchers are still squeezing out new insights from it, analysing minute fluctuations to test predictions of inflation and search for patterns that might hint at new physics. There are ongoing efforts to detect B-mode polarization in the CMB, subtle twisting patterns that could be the fingerprints of primordial gravitational waves generated during inflation. Finding them would be a massive confirmation of inflationary theory and would push us closer to understanding what came before the hot Big Bang. At the same time, the James Webb Space Telescope, JWST, is pushing our observational boundary much further than ever before. Webb is peering back into the cosmic dawn, the era when the first stars and galaxies formed. The discovery of surprisingly mature galaxies at very early times has already challenged some assumptions about cosmic evolution, suggesting that structure formed faster than expected. While Webb can't see past the wall of the CMB, its observations of early galaxies provide crucial constraints on cosmological models. If the universe formed structures too quickly, it may hint at tweaks needed in our understanding of dark matter, dark energy, or even inflation. Meanwhile, quantum gravity research is moving forward in both loop quantum cosmology and string theory. Loop models are being refined to see whether they consistently predict a bounce instead of a singularity, and whether this bounce leaves observable traces. String theorists are continuing to explore the landscape of possible universes, looking for ways to connect its vast range of solutions to the specific parameters of our cosmos. In 2025, there's also growing interest in holographic approaches to cosmology, the idea that the universe we experience may be described by information encoded on a lower dimensional surface, much like a hologram. This could provide a fresh way to bridge quantum mechanics and relativity. Another area gaining momentum is the study of primordial black holes. Some models suggest that tiny black holes could have formed in the very early universe, perhaps even as relics of fluctuations during inflation. If detected, they could serve as direct probes of conditions close to the Big Bang. Current searches, using microlensing surveys and gravitational wave detectors like LIGO and Virgo, and now LISA preparing for launch, are testing whether such objects exist. Dark energy research is also accelerating. Experiments like the Dark Energy Spectroscopic Instrument, DESI, and the Euclid satellite, launched in 2023, are mapping the distribution of galaxies and cosmic structures to understand how dark energy drives the universe's acceleration. These observations could reveal whether dark energy is truly constant, like Einstein's cosmological constant, or whether it evolves with time. If it changes, that could point toward new physics that reshapes how we think about the vacuum, and perhaps about what existed before the Big Bang. Finally, there's a growing recognition that philosophy and physics need to overlap more openly in tackling these questions. Some researchers are revisiting the foundations of probability, causality, and time, trying to clarify whether our language is even equipped to frame the question of nothing. The interplay between physics and philosophy has always been strongest at the edges of knowledge, and cosmology in 2025 is a perfect example. So where do things stand? We don't have a definitive picture of what, if anything, came before the Big Bang. But we're narrowing the options. Inflation is still the leading candidate, though being tested rigorously. Loop and string cosmologies are exploring alternatives to singularities. Observations are beginning to chip away at the vast uncertainties, and new instruments are poised to provide answers that were unimaginable just a generation ago. The mystery of nothing hasn't gone away, but the scientific conversation is moving from broad speculation to increasingly precise tests. The frontier today isn't just philosophical, it's empirical. In the coming decades, the universe itself may reveal whether the concept of before is meaningful, or whether nothing is simply not part of the cosmic vocabulary at all. At first glance, asking what existed before the Big Bang might seem like an abstract problem, something only physicists or philosophers need to worry about. But this question touches something deeper. It's about origins, and origins are central to how humans make sense of the world. Every culture, every religion, every tradition has some story about where everything came from. For thousands of years, people explained the cosmos in terms of gods, cycles, or eternal worlds. Modern science didn't erase those questions, it reframed them. Understanding whether the universe began, bounced, or has always existed changes how we see our place in it. If the cosmos truly emerged from nothing, then existence itself is stranger than anything in daily life. If our universe is one of countless others in a multiverse, then our world might be a small patch in a vast landscape. And if time itself began at the Big Bang, then the idea of before may be as meaningless as asking what's north of the North Pole. Each possibility has profound implications not only for science, but for philosophy, religion, and human identity. There's also a practical reason why this matters. Cosmology has a track record of reshaping physics in unexpected ways. Questions about the motion of planets led to Newton's laws. Questions about light led to relativity and quantum mechanics. Questions about black body radiation led to quantum theory. By wrestling with the mystery of beginnings, scientists are forced to refine their theories of gravity, quantum fields, and thermodynamics. Even if we never find a final answer, the pursuit itself drives new discoveries. On a more personal level, the question matters because it pushes us to confront the limits of knowledge. Humans don't like boundaries. We want to know what's outside the map, what lies beyond the horizon. Asking about nothing before the Big Bang is a way of testing how far science and reason can reach. It forces us to ask whether some mysteries are built into reality, or whether they are simply temporary gaps in understanding that future generations will solve. There's also a psychological dimension. Our minds are wired for causes. If a glass falls, we look for the hand that knocked it over. If a storm appears, we ask what weather patterns created it. To imagine the universe itself without a cause challenges that instinct. It makes us face the possibility that not everything has an explanation in the way we expect. That discomfort is part of what keeps the question alive, even when physics can only offer partial answers. Ultimately, the question matters because it connects science to meaning. When people look up at the night sky, they don't just see stars and galaxies. They wonder where it all came from and why it exists at all. Science doesn't give us final truth about why, but it does give us deeper and deeper layers of how. Each new layer reshapes the way we think about the universe and our place within it. So whether the answer turns out to be a bounce, a multiverse, a no-boundary universe, or something entirely unexpected, the process of searching is part of what makes us human. The mystery of nothing before the Big Bang matters because it is, in a sense, the ultimate question about existence. And even if the universe never offers a final answer, the pursuit itself illuminates everything else along the way.